Chapter 9, Lesson 4, Simulations. Two things you will learn about simulations. You will learn how to model equally likely outcomes, and you will learn how to model unequally likely outcomes. A simulation is an experiment that is designed to model the action in a given situation. For example, you could use a random number generator to simulate rolling a number cube. Simulations often use models to act out an event that would be impractical to perform. For example, a cereal company is placing one of 8 different trading cards in its boxes of cereal. If each card is equally likely to appear in a box of cereal, describe a model that could be used to simulate the cards you would find in 15 boxes of cereal. It's very unrealistic to take 15 boxes of cereal and open them all at once to see what cards you would get. So what we would do instead is create some sort of event or simulation to help us figure out what cards could we possibly get in 15 boxes of cereal. So one way you could do that, if there are 8 different cards, is you could have a spinner. So we could have a spinner with 8 equal sections, and they would be equal because it says that each card is equally likely to occur. So a spinner with 8 equal sections, we could even say numbered 1 through 8. Okay. Each number representing a different card. And because we want to find 15 boxes of cereal, we want to open those 15 boxes, we would spin the spinner. So spin the spinner 15 times. And then we could look at our outcomes from there. So this lesson is all about creating simulations. A restaurant is giving away one of 5 different toys with its children's meals. If the toys are given out randomly, describe a model that could be used to simulate which toys would be given with 6 children's meals. We could also use a spinner for this event, but let me give you a different example. We could have a bag of marbles. In that bag of marbles, we could have 5 different colors. Each representing the different toys. Okay. And we want to know the next 6 children's meals. So we would pull marbles out of the bag. Six times. But we need to put this next part with replacement. What that means is every time I choose a marble, I can record what color I got, and then I'd have to replace it in the bag, put it back in the bag. Letter C. Every student who volunteers at the concession stand during basketball games will receive a free school t-shirt. The t-shirt comes in 3 different designs. Design a simulation to find how many times a student must volunteer in order to get all 3 t-shirts. Again, we could choose a spinner, a bag of marbles, if we wanted to. So let's just choose a spinner. So we could have a spinner with 3 equal sections, numbered 1 through 3. Each number representing a different t-shirt. Now we want to know how many times a student must volunteer in order to get all 3 t-shirts. So we would spin the spinner as many times as needed until we get each number. And from there, we would see how many times it took. Mr. Chen must wear a dress shirt and a tie to work. Each day he picks one of his 6 ties at random. Design a simulation that could be used to model this situation. Use your simulation to find how many days Mr. Chen must work in order to wear all of his ties. So for this one, because there are 6 ties, I can actually roll a number cube or a die. So let's do that one. So we want a number cube with numbers 1 through 6, each representing a different tie. Okay. We could then roll the number cube until we get each number and count however many times that is. Now in this problem, it wants us to actually run a simulation. So for that, I have a simulation generator, and we're going to roll a number cube. Equally weighted, 1 through 6. Okay. Now I'm not quite sure how many times this will take, so let's do 15 times and see where that gets us. So what this is going to do is it's going to roll the numbers. It rolled a 5, a 2, a 4, so far so good, a 4 again, a 1, so we have 4 different numbers, a 3, and a 6. So let me speed up this event here to the end since we already have our numbers. And it took us 1, 2, 3, 4, 5, 6, 7 trials. So let's go ahead and copy down that table in our notes. So we have a trial and the outcome. I'm going to do my table sideways for more space. So trial 1, we got a 5, trial 2, 2, trial 3, 4, trial 4, also a 4, trial 5, a 1, trial 6 is a 3, and 7 is a 6. Okay, so it took us 7 days. Now each time you run this simulation, your answer may be different. Part 2, model unequally likely outcomes. Simulations can also be used to model events in which the outcomes are not equally likely. There is a 60% chance of rain for each of the next 2 days. Describe a method you could use to find the experimental probability of having rain on both of the next 2 days. So the first thing we need to do when we have unequally likely is we need to take our percentage and change it into a nice fraction. Percents are out of 100, so this would be 60 out of 100. I can divide by 20, definitely reduce when possible, and I would get 3 out of 5. So the probability of rain is 3 out of 5. So its complement, the probability of not rain, well, the probability of rain is 3 out of 5. The complement would be 2 out of 5 because 3 plus 2 equals 5. Okay? Now, what we could do here, the easiest thing to do when you have unequally likely events is you can have a bag of marbles with two colors. Let's just say red and green. Red can represent rain, and green can represent not rain. Okay? Then what we need to do, because we're concerned about 2 days, is we could actually pull out 2 marbles with replacement. Again, we want to pull one out and put it back, then pull another one out. And this would help us determine the experimental probability of rain happening on those 2 days. Letter B. During a regular season, let's see if I can, there it is, pens. During a regular season, Jason made 80% of his free throws. Describe an experiment to find the experimental probability of Jason making his next 2 free throws. So, let's change it to a fraction. 80 is out of 100. Again, we can divide by 20. We would get 4 out of 5. So the probability of free throws, I'm going to abbreviate FT, is 4 out of 5. Which means the probability of no or not free throws is 1 out of 5 because 4 plus 1 equals 5. So again, I like the marble idea. So we could have a bag of marbles with 2 colors. And again, any 2 colors. I'm just going to stick with red and green. Okay, and let's say red represents the free throws and green represents not free throws. You could then pull at random 2 marbles with replacement. And again, we want 2 marbles because it's the next 2 days. Letter C. An electronics store has determined that 45% of its customers buy a widescreen television. Describe a model that you could use to find the experimental probability that the next 3 television buying customers will buy a widescreen television. So again, first things first, let's change that percent into a fraction. This one we can divide by 5, and we would get 9 out of 20. So the probability of widescreen is 9 out of 20, which means the probability of not widescreen is 11 out of 20 because 9 plus 11 equals 20. You could, in this case, also use a spinner, but it's a lot harder to section off the spinners. You would have to have 20 sections, with 9 of them being one color and 11 of them being another color, which we can do. So let's try that for this one. So we can have a spinner with 20 sections, because again, 20 was our outcomes and our probability and our fractions. Spinner with 20 sections, 9 of them one color, let's say red, 11 of them another color, let's say green, okay? And the red and the green, we'll say each representing free throws and not free throws, respectively. Okay. Then we're concerned about the next 3 television buying customers. So then we could spin the spinner 3 times to see how many would be widescreen. And that's how we could find the probability. Letter D. Players at a carnival game win about 30% of the time. Based on your simulation, what is the experimental probability that the next 4 players will win? So let's change it to our fraction form. So we've got 30 over 100. Let's divide by 10. And we get 3 out of 10. So the probability of a win is 3 out of 10. The probability of a not win would be 7 out of 10, because again, 3 and 7 make 10. Now, when you're doing the experiment with a simulator like the one I've shown before, it's real easy to do whichever one you want. If you're doing it by hand, it's a lot easier with marbles. So let's choose marbles for this one. So you can have a bag of marbles with 2 colors, each representing a win or not a win. Let's say red / green again. Doesn't matter the color. Okay, and actually I'm going to add in here, there would be 3 red and there would be 7 green. Okay. Then you would pull out marbles at random with replacement. Again, we pull it out and then we put it back. We are concerned with 4 times, so 4 times. And this question wants us to actually do the simulation, so let's pull out the simulation tool. And we chose a bag of marbles. We want, looks like we're going to have to use red and blue in the simulation, which is not a problem. You can leave it at green though, we'll just use blue. We have 3 red and 7 green, so let's make that 3 red and 7 blue. Okay. We are concerned with the next 4 trials. So let's see what we get. Blue goes back in, blue, back in, blue for the 3rd, back in, and blue for the 4th. So our table here, which we can copy down, we have our trial and our outcome. So trial 1, we got, remember we're using green. Trial 2, green. 3, green. And 4, green. Now red marbles are a win. And the question wants to know the probability that the next 4 players will win. Well, I have 4, so probability of a win, and this is experimental, equals It's out of 4 outcomes, and I have 0 wins. So the probability of winning is 0 or impossible, and that is the experimental probability. If I were to run this experiment again, I could get 0, I could get 1, I could get all 4 red. It can be many different things. Now, if I repeated this trial or this experiment several more times, perhaps 20, 50, 100, 200 times, we would see that this experimental probability would be closer to our theoretical probability. Just to show you here, let's reset this and try it again. This will do it fairly quickly. So again, we had 3 and 7. And let's do 100 trials. And what we're going to do is I'm just going to skip to the end and look at our table. So we actually did get some red here, okay? We had some red a couple times. And the probability here, we got 33 reds and 67 blues. Our experimental probability is approximately 0.3, which is close to 3/10. And our probability of our green is 0.67, which is close to 7/10. So as the more trials we do, the closer our experimental probability will come with our theoretical probability.